Now we're recording. Now it'll animate. Okay, so there's your answer. And let me see what you guys voted for. Yeah, most of you got that one right. Uh, what's the dynamic concept that puts together speed and direction? Velocity. What's the dynamic concept that puts together distance and direction? Displacement. All right, now what we're going to do today is talk about adding vectors up. And you know what? Take really careful notes and listen like your life depends on it, because we are going to be doing this until the cows come home all semester. And next semester, when you're in 2054, or whenever it is that you take 2054, you're going to be doing vectors out the wazoo as well. All right, now, I'll just, while you guys are getting your notebooks ready, I'll just make a point. I was studying, I was putting together the lecture for today, and I was studying the book, and I was putting comments in there. I put in some highlights, and I put in some, I think they call them annotations, comments. And I believe you can read those in the UCF version. Anybody seen my highlights and comments? Okay, so it's possible for you to see it. And psychologically speaking, it's pretty important for you to be aware of what the things that I think are important. Then my comments in the textbook, because if you think about it, the exam, midterms and final, I can't ask you everything I would like to, right? Just like in lecture, I can't lecture over everything I would like to. So in lecture and on exams, I have to pick out the stuff that I think is most important and make sure to go over that. Okay, same with exams. My lectures are an expression of the things that I think important. So are my exams. The difference is that on exams, you are trying to show me that you understand sufficiently the things that I think are important. All right. Now I have a PhD in theoretical astrophysics, so that's our society's verification that I am fit to make those decisions about what is important enough. Okay. Now it may be slightly different from other instructors, but most of us in the physics department are going to concentrate on mostly the same things. All right. So on an exam, you're going to be trying to think about the things that I've had in lecture, and those are the things that I think are important. So anywhere else you see me expressing things that I think are important, i.e. the textbook, the UCF customizable version, you want to make sure that you're aware of all that stuff. Okay, and when you do, don't drop your clicker all over the floor. So here's another one. And I don't know if you guys missed it or not, but the talking PDFs are pretty important. Those are other things that I put together for you. Make sure that they're in talking PDF form, not just in PowerPoint, because I think they're important. All right. Now there's another one up. I put the homework 1 solution up today in the .cam page. There's now 2 lists. So keep that in mind as we go through the examples in lecture and also in the textbook. Okay, chapter 3.2, this is example 1. Now, 3.2, they're going over the way that you would do things with a protractor and a straight edge and graph paper maybe. Okay, in other words, graphical methods, which are kosher. You can definitely do that, but you got to be careful. You can't be shaky. Oh my goodness. Some of your guys oh, you know what? There was somebody that had a hand-drawn velocity graph, and it was inspiring. Seriously, it wasn't, it didn't look, some of you guys it was all, colored pens and stuff, all that stuff. This guy just had pencil, and it was a little wobbly looking, but he had everything he needed, and you could see that he put in a lot of thought into it. And I thought, but, this is the one, this is my favorite velocity diagram, velocity graph. So anyways, let's get down to this chapter 3.2, graphical methods. So the example is, okay, a lady takes a walk, and her three legs of her walk are, given in meters with a direction. All right. So 25 meters in the direction 49.0 north of east. There it is right there. Okay. And all these vectors are proportional. Now, in no particular location, I sketched in the second leg, B, vector B. It's a little shorter, and it's 15 degrees north of east, so not quite as tilty, all right? And it's in the textbook, so you can look it up. And they explain it nicely. And my explanation today, going through it, will be a little different from that, and hopefully between the two, you'll get a good concept. Now, in no particular location, here's the third one. Now, the reason I'm separating them out in kind of random locations on the page is to emphasize that graphically speaking, what you must do is put them all together. And I'm going to animate that for you. So vector C, the third and final leg of her walk, is 32.0 meters, direction 68 degrees south of east. So she's dipping below the east. And that little compass I had shows you where the east, west, north, and south are. All right. Now, the method for graphing them up on graph paper and adding and forming a vector sum, which is what we're doing here. The main tactic is to place them head to tail. All right. Now, here's how you do it. You take the tail of vector B and you park it over there at the tip of vector A. Right? Just like that. And no matter what the directions are. And you can do this when you're sketching in your notebook and stuff. Just try to, make a fairly good sketch. But I measured this out really carefully, pixel by pixel. So this is kosher. This is right in line with the textbook example 1. The lady takes a walk. Now you take your third one, vector C, and get the tail of vector C up to the tip of vector B. If that's all your displacements, all three legs of your walk, then you're ready to complete the task. And that is to draw the resultant vector from the tail of A to the tip of C. All right, tip of the last one. All right, so here it is. Now, if you want to look at it, I'm going to burn it in. Here it comes with flames. All right, so there's your resultant, R. And if you have a protractor and a straight edge, you can estimate the length of that vector R with a straight edge. And with a protractor, you can kind of figure out, 10 degrees south of east or whatever it is. All right. And that expresses this vector sum. So go ahead and write down this vector equation. The sum of vector A plus vector B plus vector C is the resultant vector R. The textbook uses R for a resultant vector, at least in this chapter. And resultant is a concept that we're going to really need because it turns out that, as we'll talk about on Friday, Sir Isaac Newton's idea about forces requires us to figure out by vector addition the net force on an object. So if these were three different forces, you would do the same thing, and then vector R would be the net force. So you get a little bit of northeast force and then a little bit of southeast force, and then the resultant is slightly dipping in the southeast direction. All right. Now, Another thing that they mention in the textbook is the resultant R is independent of the order in which you go tip to tail. All right, now I'm going to show you how that works. All right, so the next screen is my three vectors again. Okay, you should resketch them if you want. All right, or just do a new sketch. And what I'm going to do is first, instead of doing ABC, I'm going to do ACB. There's C, tail of C. Go ahead and sketch this. Okay, it's an important concept to see visually. So the tail of C goes to the tip of A. And then, all right, I still have one more vector to add in there graphically. So I copy it, the tail of B onto the tip of C. And guess what? Now I go from the tail of A to the tip of B, because B is the last one that I added in. All right, so, and guess what? Ding! Exact same vector. Although when you put all the three constituent vectors together in the diagram looks different, but the resultant vector R is the same. Okay, and this would be the formula: vector A plus vector C plus vector B still equals vector R. No difference. Right? If you're doing it carefully. Question. Is there ever an instance when one vector affects the other? Not really. Because what you're doing is you're adding up velocities, or you're adding up displacements, or you're adding up electric field vectors, or you're adding up all the same thing. So they're just going to be more of the same. In other words, you wouldn't add a force vector and a velocity vector together, tip to tail type of a thing. You know, and magnetic forces, for instance, are dependent on the direction of the velocity and the direction of the magnetic field. So in that situation, you have a fancy equation, but you still don't add up a force to a velocity. Okay, the velocity controls the force in a given magnetic field, and it can be tough to graph that stuff up. But you don't do this, not necessarily. You know, you might have an electric force and a magnetic force that you got to deal with moment by moment. But you wouldn't add. It's like, you know how your parents would say, or your second grade teacher, don't add apples and oranges. You know, that's famous. You know, so don't. You know, if you're adding apples to apples, just add them up. Okay, and it's just, you got more of the same. And you got more displacement, you got more velocity, you got more force. Whatever you're adding up, you just got more of it. But if you're adding forces and velocities, you got I don't even know what that is. It's a mess. So Sir Isaac Newton just says, don't do it. So don't do it. Now, questions about this graphical method? It's outlined nicely in the textbook. All right, let's keep going. Now I want to talk about analytical methods. This is chapter 3.3. By the way, I have a list of problems that I like from chapter 3, and I'll try to post that tonight as well for study purposes. So it looks like our exam number 1 is going to be heavy on chapter 2 and 3, and as much of chapter 4. We won't complete chapter 4 on Friday, but we'll dip into it as much as we can, and as much as we can do Friday in chapter 4. That's what we'll have on exam 1. So guess what? This is going to be on there. This diagram is very, very important. Analytical methods, as they say in the textbook, instead of doing a graph paper, straight edge protractor, you make your own sketches and let the trig do the talking. All right? And that's what you would normally do. So that's why engineers and stuff and physicists, they don't have to be a second Leonardo da Vinci as for drawing perfectly proportional diagrams and stuff. You can draw like the student whose velocity graph was so inspiring. You can draw something that's shaky looking and then let the numbers do the talking. And that's what this is going to do. Now, we've already done some trig in the trig workout talking PDF from last week, or actually I think it was 2 weeks ago. This particular diagram is figure 2, chapter 3.3. Just try to mesmerize it. It's just, AY equals A sine theta, AX equals A cosine theta. The theta is the tangent of AX over AY, or the inverse tangent of AX over AY. We're going to do this out the wazoo here on the document cam in a minute. All right. Now, this particular diagram, figure 2, the two vectors, AX and AY, I don't usually express them as vectors, but this diagram does. And I think it's okay to do that. The two constituent vectors, or the two component vectors, parallel to the x-axis, parallel to the y-axis, are drawn in red with the dashed lines. AX down on the x-axis, AY over to the right, parallel to the y-axis, which is over on the left. And those two together, the tip of tail of AX to the tip of AY is your resultant vector. So vector A is, go ahead and make a note of this. Vector A is the resultant of vector AX plus vector AY. All right. Now, I've been doing this for many, many years, so I see your question in the back. Hold on a second. I've been doing it for many years, and so I just draw triangles and label them and stuff. I'm not that fussy about it, but the textbook is I was watching, reading it, and I thought, boy, these guys are doing this very carefully and nicely. So I highly recommend the textbook. Question all the way in the back. Repeat. Repeat about vectors. Yeah, vector A is the resultant of constituent vector AX plus constituent vector AY. All right. We just did, what's your name up there in red? Jasmine? Okay, Jasmine, we just did vector A, B, and C. We did vector A plus vector B plus vector C equals R, vector R. And then we did vector A plus vector C plus vector B equals vector R. Okay, this one just has two vector constituents, right? But it's still, you can think of it as a resultant. And so a lot of times you put together the results, and sometimes you have the vector A itself, and you want to break it down into the two X and Y components. And analyze those for various reasons. Now, here's a typical problem, and I want you to draw this sketch carefully. X and Y axes, and notice that they have the four directions of the compass: north, east, south, and west. North is upward, east is rightward. And they have a big resultant vector made up of two constituent vectors, A plus B, A and B. A is in red, B is blue. All right. Now, if you're given two vectors, A and B, like this, and you want to construct the resultant vector, you can do it. All right, and that's what we're going to talk about. Question up here. Yeah, A and B are not distances. They're not really specified as velocities or displacements or anything. Just think of them as velocities. R is like the net or but the textbook author calls them resultants. But eventually in chapter 4, he's going to start calling it the net force because that's what we're going to be talking about, forces. Anyway, so you have given vector A, and given vector B, what's the resultant? You know, so so here's your basic strategy. What you do is you break it down into right triangles and then rebuild the resultant. All right, so for instance, vector A, here's a right triangle in blue, all right? The hypotenuse of that right triangle is vector A. So the AX is the horizontal part of that right triangle. AY is the vertical part of that triangle. Now, I'm not going to add those to the diagram, but you can if you like, right? But here, for the second triangle, here's the other, or the second vector, vector B, here's the other right triangle, all right? And so when you're trying to figure out what R is, the resultant, you can focus on your two constituent vectors, form two right triangles like the blue and the pink, and then rebuild it all together into the resultant. All right, so here's the x component of vector A, or vector AX in the textbook terminology. And here's this corresponding BX of vector B. And then here's the AY vector, the vertical side of that blue triangle, for vector A. And if we do a little trick, we can figure out, how many millimeters that is, or how many meters, or how many light years, how many meters per second, whatever the quantity is it's kind of generic right here, but we're going to do an example in distances. And then here's BY, the vertical side of the pink triangle. Now, sometimes you got more than one. I mean, if you have three vectors, you just draw another set of triangles, and they might overlap, but you can always kind of break it out, onto another piece of paper. Just, like I say, analyze. To analyze means to break things apart. So split off your triangles and just study them. Do the trig of each one, and then put it together, and you get R. All right. So the horizontal components and the vertical components of the constituent triangles, that's what builds the resultant. All right. Now, I'm going to ask you a couple more clicker questions. So turn on your clickers. And just to get you thinking about components, by the way, this is the first day of official class participation. And I notice that not all 288 students registered for this class are clicking. I only had 200 the last question, so hopefully it's a few more now. But here's your question number one. Which velocity vector in this set has a component of 0? And only one of them does. Good. That's good. I see you guys pointing at the vectors and stuff, talking with your neighbors, going like this with your hands and stuff. That's lovely. Because that means you're thinking. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Oh my goodness. Yeah. Yeah, that's not a hard one. Which is for the basketball velocity, is the x component or the y component 0? X. Okay. All right, next question. Which one has a negative Vy? They all have some Vy. Which one has negative Vy? 15 seconds to vote. 10, 9, 8, 7, 6. Because this one should be cinchy. 5, 4, 3, 2, 1, 0. Uh-oh. We got some splaining to do. Okay. Most of you voted for the correct answer, which is Spaceship U. But a few of you, okay, I see what you're doing. A few of you voted for T-Rex. T-Rex does have a negative component, but it's not Vy. It's Vx. All right? So be careful as always, on my homework, on my exams, and my clicker questions, read carefully. You cannot go without it. Now, what we're going to do is a full example on the document cam. And this is example 1. Let's see, what time is it? Oh my goodness. 4:16. I tell you what. We'll just talk about this. We'll talk about feelings and stuff instead of doing the sketches. You've got, what we want to do is figure out the resultant of these two babies. And, one of them's only tilted 20 degrees. So it's going to, the first one, A, it's going to have a little bit more displacement to the east than vector B. Now, vector B is going to have a lot of northward displacement. So we're going to get a mixture. But, we don't have anything to the left, to the west, and we don't have anything negatory to the south. So whatever we get, it's going to be somewhere in the... I was in an accident yesterday. Hurt my hand, my left hand. It's like powerless, like kryptonite. Anyways, so we're going to get something up in the first quadrant. All right, now, here's what I'll tell you what I'm going to do. I am going to do a talking PDF at home tonight and of this problem, and it'll be a little different. It's worked out in the textbook, but it'll be a little bit different. It'll look a little different than what they do in the textbook. And so you can have those two together. Also, tonight I'll put the PDF for written homework 2, and I already know what the problem is going to be. So be ready, and I'll see you guys on Friday. Yeah, see ya.